All right, Highlanders, how we doing? Section 12.4. This is something that I think that you guys are going to like because, again, it's something that you have done in the past. You have done limits at infinity in Honors Algebra 2, and you also did it with me. So 12.4 is important because it really is going to help us understand how to do 12.5 and leads to the idea of an integral. So it does correspond with 12.5. It should be a quick section for you. But still I want to go through and make sure that we all completely understand how limits at infinity work. Remember, when we start looking at limits at infinity, for example, something like this particular inverse variation, we know, or we should know, that x can't be 0 and y can't be 0 here. And this is a hyperbola. It looks like this. So when we start looking at the limit as x approaches positive infinity, and the limit as x approaches negative infinity, we understand, and again, we looked at doing this as far as end behavior of the function is concerned. So really, when we start talking about limits at infinity, we start looking at horizontal asymptotes. And remember what I told you about horizontal asymptotes. They're really all about end behavior and what's happening. Are we approaching a value, or are we going to positive or negative infinity? And with our work with limits, we understand that to have a limit, we have to approach a value. So looking at this particular example here, our inverse variation, we know that as we go to positive infinity, my function as x is getting bigger, y is approaching 0. And as we go to negative infinity, we're approaching 0. So the limit here of this particular function at infinity is 0. And that's what it's approaching. Okay. So to kind of get us in the right frame of mind, what we have learned with particular rational functions, which is what this is. Remember, we've got three cases here. First case. So case 1, where the degree of the numerator is less than the degree of the denominator. And this is really what we're talking about here. We're talking about rational functions when we're looking at limits at infinity. So if the degree of the numerator is less than the degree of the denominator, for example, if we've got 3x squared plus 4x over 5x cubed plus 2x squared minus 1, just for example. My degree on top is a degree 2 over a degree 3. So when the degree on top is less than the one on the bottom, right, we know by rule that this has to go to 0. So the limit as x approaches infinity of f of x, in this case, it's going to 0. And that's always the case when you have a rational function, and again, a rational function, in case you're wondering, polynomial over a polynomial. So in this case, we have a horizontal asymptote. The degree on the top is less than the bottom, so we're going to 0. Let's just take a look while we're doing this of what's really going on here. So I'm going to look at the limit as x approaches infinity of this particular function. So I can kind of show you numerically what's happening here. I know I've done this in class, but just in case, I'm going to take this top numerator here, and I'm going to factor out an x squared. So I'm going to take out the x squared, and that's going to leave me 3 plus 4 over x. And I'm going to look at the bottom, and I'm going to factor out the x cubed, and that's going to leave me a 5x plus 2 over x minus 1 over x cubed. And then when I look at limits at infinity here, I know that this right here reduces to 1, so I have 3 plus 4 over x times 5x plus 2 over x minus 1 over x cubed. So again, then implying the limit, we know this goes to 0. We know this goes to infinity, this goes to 0, this goes to 0. Oh wait, this is, I'm sorry. Now this is gone, right? This is gone. So that's just 5. So we end up with what? We end up with this, if like in a reduced situation, approaching this. Which, like our original example, sorry about that, the original example of this, right, my inverse variation, when the degree on the bottom is bigger than the top, is the same as this. So really, as we know with all polynomials and with end behavior, we don't care about what's going on with that, because when x gets really, really big, those leading terms take over, which is what this is kind of illustrating here, is that, you know, when you have $1 billion, 5 cents really doesn't matter to you. Right? So when we look at this and it reduces to this, which again is this situation up here. So we're going to 0. So this is case 1. Anytime the degree of the numerator is less than the denominator, we're going to 0. Period. It's going to 0. Because, again, numerically speaking, this is going to grow faster than this. So the thing has to approach 0. Period. All right, case number 2. What happens when the degree of the numerator is equal to the degree of the denominator? And again, using that same logic, let's say we have 3x squared plus 4x minus 7 over 5x squared minus x plus 9. So we notice that the degree on top is 2, the degree on the bottom is 2, and with all polynomials, that doesn't matter. So really, when we're looking at the limit as x approaches infinity of f of x of this particular function, we're really looking at this, because the rest of this doesn't matter. Which means that cancels, and what are we approaching? 3/5. So the overall rational function is going to approach 3/5, and that's your limit. Okay, so these two cases, case 1 and case 2, are really the two that are going to help us throughout the process in 12.5. And that's really important, because if we have a limit at infinity, that's when we can actually approach values like 0 and like 3/5. Because in case 3, when the degree of the numerator is greater than the degree of the denominator, the limit does not exist. And if you remember, we spent time talking about oblique asymptotes or slant asymptotes here. When this was one more than that, we do the division and find the slant asymptote. That was for end behavior, but even if you have a slant asymptote, remember the graph was doing something like this. No, I'm sorry, not like that. But it was doing something like this. Whereas when you look at the end behavior here and here, right, it's going to positive and negative infinity, not a value. Right? And we know and we've learned from our limit process that if we approach positive or negative infinity, limit does not exist. And I don't care about the slant asymptote here because I'm really looking for the limit. So just remember that when the numerator is bigger than the denominator, limit doesn't exist, move on. No issues. We don't have to find slants, asymptotes here. We're not doing any of that anymore. All we care about is finding limiting values. So it's either going to be a situation where we have it approaching 0, like in this case, or that's less than that, or it's approaching the leading coefficients when the degrees are the same. Those are the two cases we're concerning ourselves with. And whether we have functions or we have Sequences, no different, right? Because I could have a sub n equal 4n, n plus 3, 2n plus 3 over 3n squared times 2n plus 1. If you notice, the degree on the top is third, right? It's a third degree. And the degree on the bottom, third degree. And again, when that's the case, applying what we've learned up here, if I'm going to find the limit as n approaches infinity of a sub n, all I need to concern myself with is what is that leading coefficient, right? What is that leading coefficient? Because that will lead to my limit. So this is important, gang. So when I have something like this, do I have to multiply everything out? Do I have to simplify everything? Heck no. Don't need to, right? Because all I care about is the first term. I don't care about what the n squared term is, what the n term, because none of that matters at infinity. And that's really, really important to understand. I know if you were sitting in regular pre-calc, they would make you expand all that. They would make you get a simplified polynomial and a simplified polynomial here, and then take a look at the leading terms. It's a lot of excessive work, and it's not necessary, not for honors kids. Okay, so let's keep in mind, what are we concerned with here? Understanding conceptually that all we care about is what the leading coefficient is, then this becomes a very simple, easy process. All right? So how do we find that leading term? By taking this and only doing that first distribution. That's it, right? I want to know what that n cubed term is, so I got to multiply the three n's together. So I have 8 n cubed over 6 n cubed. Again, the rest of this I don't care about, because infinity, it doesn't matter. So what's the limit? 8/6 or 4/3. And we are done. Right? Because remember, when you're looking at limits at infinity, only the leading terms matter when your degrees are equal. So with sequences, again, if it has a limit, the sequence converges. If it doesn't have a limit, then the sequence diverges. All right, so that's pretty much all of the notes. Let me add a couple things. I just mentioned something about divergence, so let me go through that with you as well. Let's say we have this particular sequence, 3 times to the n minus 1. Hopefully you recognize that as a geometric sequence, and it has a growth factor of 2, right? 2 is the base here. So if we were to take a look at a few terms, trying to determine if this sequence were to converge or diverge, the first term would be 3, because we plug in 1. Remember, it's a sequence, so that n is the set of natural numbers. 1, 2, 3, that's your domain. Okay, so the next term would be 3 times 2 or 6, times 2 is 12, times 2 is 24, etc. What's happening here? This particular geometric sequence it's getting bigger without bound. So the fact that it's getting bigger without bound means this thing diverges. So what's going to happen with the limit at infinity? It's going towards infinity. It's getting bigger without bound, so there is no limit, or the limit does not exist here. However, if you remember our geometric sequences, well, let's not make that, whatever, doesn't matter. Remember when that r value right there was less than 1, greater than 0? What do these values look like? First term is 3, 3 halves, 3 fourths, 3 eighths, with the denominator doubling. This is going to what? it's going to 0. So this sequence converges, and your limit is 0, which again, that is where that horizontal asymptote is. In 12.5, we're going to look at this, but not necessarily looking at sequences. We're going to be looking at series. And those formulas that I had you guys memorize or look at, those are going to come back into play. But we'll get to that when we get to 12.5. All right, so let's practice our limits at infinity here. I'd like to look at this first example, which is the limit as x approaches infinity. And again, pay attention to some of these examples because there's a couple things here I want to point out. And we have 1 plus 5x over 1 minus 4x. And we have a rational function. And again, these terms right here don't matter when we're looking at infinity. All we really care about is the leading coefficient. And in this case, because the degrees are the same, we're approaching negative 5/4. So you're going to be doing a lot of that. Next example. Let's take a look at the limit as x approaches infinity of 4x to the 4th over x squared plus 3. And that's a 4. So in this case, what do we know? The degree on top is bigger than the degree on the bottom. Limit does not exist. And again, that's why I said the homework here. Make sure you do it, but these problems are quick if you know what you're doing, right? All we're doing is evaluating limits. All right, next example, number 28 in the book is the one I'm doing here. We have the limit, and this is an important example, so pay attention as x approaches infinity of x over 2x plus 1 plus 3x squared over the quantity of x minus 3 squared. So the first thing we need to determine here is that we have a sum. And again, if you were sitting in a regular pre-calc class, they would make you add that together. They would make you simplify the numerator and denominator, and then you can just zero in on that leading term and determine what the degrees are. Okay? But there's a property here. And we talked about this property before when we were doing derivatives. We have a sum, right? So the limit of the sum, I'm going to write this down, the limit of the sum is equal to the sum of the limits. So the limit of the sum is equal to the sum of the limits. And we have a sum here. So the limit of the overall sum is equal to the sum of the individual limits. So we can look at this as two separate limit problems. So for example, I can look at the limit as x approaches infinity of this plus the limit as x approaches infinity. And if this process looks a little familiar, it's because when we were working with our series stuff back in chapter 9, this is what we kind of did with our sigma. Remember, we broke it up and we broke it up and then we applied formulas. Hopefully you do. If not, we're again, that's a lot of what we do in 12.5. Okay, so now if we look at the limit here, degrees are the same. So this particular limit is 1/2 because we take the leading coefficients. Here, degrees are the same, so be careful here, right? If we were to expand this, this would be an x squared on the bottom. So the leading term here, and again, you don't have to expand that unless you feel like you need to. I'm just going to do that real quick. Negative 6x plus 9. Do we care about that? No, we don't. All I care about is that these are the same, so the limit is 3. So what is your overall limit? 3.5. Now, do you have to write this out? Hopefully not. I wrote it out just to make clear what I was saying. Find the limit, add them together. Okay. Next example. All right. So a sub n equals 3n minus 1 factorial over 3n plus 1 factorial. All right, so do you remember simplifying these? For us to be able to determine the limit at infinity, as n approaches infinity, we need to make sure that we know what the degrees are, top and bottom. So remember what the factorial does, right? It drops it down by 1 each time. So this becomes 3n minus 1 times 3n minus 1 or minus 2 times 3n minus 1 minus 1 or 3n minus 3, right? And it all goes down to 1. So as we go minus 1, minus 1, minus 1. Just a refresher, 10 factorial is 10 times 9, right? Times minus 1 times minus 1 until we get to 1. That's what we're doing up top. Subtracting 1 each time. The bottom, we have 3n plus 1 times 3n plus 1 minus 1, or 3n, times 3n minus 1 times 3n minus 1, etc., all the way down to 1. So what we notice happening here, gone, all of that's gone. What's left? 1 over 3n plus 1 times 3n. So when applying the limit to this particular function, we see that the degree on the bottom is bigger than the degree on the top. So we know that that particular sequence converges to 0. So again, same rule, right? Same two rules we keep applying here. All right. Let's take a look at 48. We have a sub n equals negative 1 to the n plus 1 over n squared. Now, hopefully you remember what this does. This right here, because it's negative 1, when that power is odd, we're negative. When it's even, we're positive. And all it's doing is alternating the sequence. So, hopefully you're looking at this and you're saying, well, okay, I know what that limit is. If not, write out a few terms. Remember, n starts at 1, then it goes to 2, then it goes to 3 because it's a sequence. So when n is 1, this is 2. So negative 1 squared is 1 over 1. That's the first term, right? When n is 2, this becomes odd, so it's negative 1 over 4. When n is 3, this becomes even, 9. So we can see that the next term is going to be, right? So what's happening is the degree on the top, regardless of it alternating, the degree on the top is 0. The degree on the bottom is going to be 2, right? We're squaring. What's happening here? Even though it's approaching it from above and below, it's still going to 0, so the limit as n approaches infinity of a sub n is 0 in this case as well. Okay? So what I'm suggesting here, if you're looking at something that's sort of a different type of sequence, something we've looked at and understood, but when we're looking at a limit at infinity, if we don't know by looking at it, write out a few terms. Look for the trend. If you see the trend getting smaller and smaller, you know it's going to 0. Okay, so now the last two examples that I have for you in this section are two of the most important examples because they lead directly into 12.5. So the first one, my function is a sub n equals 4 over n, parenthesis, n plus 4 over n, bracket, n times n plus 1 over 2. And you might be looking at that saying, that's ugly. So hopefully this you recognize. That's the n times n plus 1 over 2. That's Gauss's formula, right? The n over 2 times n plus 1, that's the sum of the integers. This right here is going to be something we're going to talk about as far as having the width of n rectangles, but that's for the next section. All we really care about is what is the limit as n approaches infinity of a sub n. Does it exist? If it does, what is the particular value here? And keeping in mind, do we need to completely simplify this? No, we don't. But this 4 over n is being multiplied to this entire series here. So what's important is I would probably, if I were doing this, is I would go ahead and make this a little bit easier to look at by distributing that 4 over n. So that's going to give me 4 plus 16 over n squared times n plus 1 over 2. And again, the limit of this particular sum is equal to the sum of the limits. Here we have a constant. So the limit, as it approaches 4, remember a constant's like a horizontal line, no matter what x is, no matter how big x gets, is always going to be 4. So the limit of this, or the limit of any constant, and that's one of our properties, right? And I'm just going to write that down here real quick. The limit as x approaches infinity of any constant c is c. So let's not forget that. I'm also going to write down another property that's important. The limit as x approaches infinity of 4 times some value like 1 over x. Right? So if we're looking at that, remember, is going to equal, we can pull this guy out. So let's not forget that as well. And that's it for now. We'll talk more about those other properties. But remember, this guy can get pulled out. I probably should do this, but that's okay. So looking at this, right here, I can look at the sum of the limits. So I'm going to find the limit here, and I know that's just 4. And then I got to focus in on this guy. So looking at the numerator, that degree is n squared, denominator n squared. So we know we have a limit because the degrees are the same. The question becomes, what is the leading coefficient? The leading coefficient on top is 16, right? So if I'm looking at this 16n squared, the leading coefficient on the bottom, 2n squared. So what's the limit of this particular rational function? Without really looking at simplifying anything, I know that it's 8, 16 over 2. So the overall limit at infinity, 12. I know that is approaching 12. Okay, so what did we do? We took this outside particular fraction and distributed it to these two terms because it's an overall multiplication, and that allowed me to get this and this, and then I had a separate sum, so I could just evaluate each individual limit, which made this problem really easy. And again, it looked ugly, but all we're doing is looking at two limits. It's a simple arithmetic, and we're good. Okay, last example in this section. We have, and I'm looking at question 52 here. We have a sub n equals n times n plus 1 over n squared plus a negative 1 over n squared oh, sorry, that's n to the fourth, times n plus 1 over 2 squared. So again, in this particular case, what we see this formula kind of arising, if you remember, that is the sum of the integers cubed, which was the square of Gauss's formula. And so we have a sum. So really, if I'm looking at the limit as n approaches infinity of a sub n, I'm really focused in on these as separate problems, because I'm going to say it once again. The limit of the sum is equal to the sum of the two limits. So ignoring this for right now, the limit here, does it have a limit? The degree on top is 2. The degree on the bottom is also 2. So the leading coefficient on top is 1. The leading coefficient on the bottom is also 1. This limit at infinity then is 1, right? Those are your leading coefficients. All right. Then I'm looking at this guy, and I have to see, this is n squared, this is n squared when I square both. So the leading coefficient up here, this is 1n squared times 1n squared is going to be 1n to the fourth times a negative 1. So that's negative 1 on top. That's the leading coefficient on top. And then the bottom is 2n to the fourth. So I did that kind of quickly. Let me go through it one more time. Looking at this whole thing here being squared, I have an n squared and an n squared. That's n to the fourth, which matches the bottom, which means the degrees are equal. So I have a limit. And since this is negative 1, and there's no numbers in here that I have to worry about, so that leading coefficient is negative 1n to the fourth on top, and on the bottom is 2n to the fourth. And remember, when multiplying, we always multiply straight across, so let's not forget that. So we see negative 1/2 becomes my limit for this particular function. So the overall limit is the limit of the sums. 1 minus 1/2 is 1/2. Okay, gang. Hopefully, I've tried to give you some clues on where this is all heading, which is why I wanted to spend some time going through. We are going to use these summation formulas when we go into 12.5. And so I will start 12.5's lesson with those formulas again. We'll take a look at them and how we use them to find the limits. I'll go through the whole limit process of finding the area under a curve and look at some examples. I hope this helped. Don't forget to do your book notes. And like I said, 12.5, this is the biggest problem. And what did it, if you know, like I said, by the time you get there, probably going to take you 10 seconds of problem. So 12.4 should be done quickly. But also take your time here, because if I were to take a look at this particular same problem, if this had a 2 here, then that changes everything, right? Because then this limit becomes a 4 on top. So I get a negative 4 over 2, which then now I've got 1 minus 2, which is negative 1. So pay attention to any of the numbers that are coefficients on the variables, and if you're squaring or cubing. Okay? All right, that's 12.4. Lambo out. Have a great day.